Perfect. So, yes, welcome everyone to the Provable AI Safety Seminars. So for context, this is a monthly session where we discuss research and development about AI safety involving formal methods and mathematical proof, safety guarantees, and other interesting related topics. The session is 1 hour and the format this edition is a talk followed by questions and answers and discussion. Um, and yeah, our speaker is Steve Omohundro with a talk titled Provable AI Safety. So the floor is yours.
Great. Thank you so much. Thank you all for being here and looking forward to discussion afterward. I'd like to go through the slides just because there's a ton of material. So my agenda for today is to start by arguing that powerful but unsafe AI is already here, that the current AI safety approaches are insufficient for the challenges that we face, and that we must in fact use mathematical proof and the laws of physics to have true safety. I'll talk about ways of using mathematical proof for provable software, then provable hardware, then provable social mechanisms, and end by arguing that we must choose the path of human thriving. So let me start by just saying the recent Llama 3 model from Meta, just released maybe a few weeks ago, I believe represents a game changer for AI in both AI capabilities and AI business and for safety and risks. They are releasing 3 models, an 8 billion parameter one, a 70 billion, and a 400 billion parameter model. Apparently, they spent $30 billion on the GPUs to train this. The 400 billion model is not released yet. It will be sometime this summer, but an early checkpoint of it is apparently the same qualities, GPT-4 Turbo, Claude 3 Opus, and Gemini Ultra. And this is what's a game changer, that we're going to have open source models which are at the leading edge of the frontier commercial models. One very interesting thing about how they're doing this is that they've trained it on 15 trillion tokens. And for the 8 billion parameter model, that is 75 times the chinchilla scaling that's sort of optimal for if you want to use your compute and you want an 8 billion parameter model. And so that means that this 8 billion parameter model is way better than typical other 8 billion parameter models. Inference is about 20 to 40 times cheaper than GPT-4 because it's open source. It's already running and a whole bunch of people are serving it. Fine tuning, which means you can take this base model, which is trained on tons and tons of data, and fine tune it for your application using something like QLoRa. And there are now groups that are showing how to do that on video cards at home. So that's become a capability to sort of create world-class specialized models pretty much anybody, anywhere in the world, in any country, for any purpose. In the first week of releasing these models, there were 1.2 million downloads. So I think this is really a radical change. It enables dramatic improvements in capabilities. It undercuts the business model of OpenAI, of Anthropic, and many of the other companies because Meta doesn't sell AI. They use it, they sell ads. And this is a classic business thing called commodify your complement. So I think it's huge there. But because we now have very powerful open source models, I think it dramatically increases the risk landscape. And I'll say a lot about some of the shifts there. Just as sort of an example of the potential impact, somebody already within the first few days has the 8 billion parameter model running on a $93 Raspberry Pi 5. And I believe there are almost hundreds of millions of these machines out there. And so we should expect hundreds of millions of copies of powerful AIs all over the world. AIs are these large language models. Stanford High recently did a big analysis of the current state of the art, and they're arguing that basically LLMs are already better than humans on many tasks, and they're all kind of converging, this year to human level performance on a lot of things. This study shows that LLMs are 81.7% more persuasive than humans. So they, try to get an LLM to convince somebody of something and get other humans to convince them, and the LLM was far better. And so that means there's huge motivation to use these models in sales, recruiting, manipulation, elections, warfare. And one tragic example of that is a young man who killed himself as a result of an interaction with a chatbot that encouraged him to do that. And so my takeaway is that vulnerable people should not be communicating directly with uncontrolled AI. So I think that model that, oh yeah, AI is something you just talk to and you train them on the whole internet and then you let them talk to anybody is not going to fly. It's a disastrous model. Um, LLMs are also being used and very powerful in cyber attacks. There was a paper that showed that if an LLM agent reads about a one-day vulnerability in a system, it can generate the code to exploit that vulnerability. And there's a big literature review of how LLMs are currently being used both to attack systems and to defend them. And so I think we should expect that this trend is really going to go forward. We should expect widely available open source AIs which can exploit the vulnerabilities of every common system. So today, a system might have a vulnerability, but the people that know about it and have the skills to exploit that vulnerability, it's a fairly rare capability. I believe that with these models, everyone can have one, and I'm sure groups are going to create specialized AIs which are for cyber attacks, and so that dramatically increases the risk of cyber attacks on systems. The NSA released a reverse engineering tool a few years ago called Ghidra, very sophisticated, allows you to look at binaries and find, exploits and so on. But it requires a lot of skill to use it. Well, somebody just hooked up a large language model knows all about Ghidra, and so now you need to know anything to use it. And so I believe pretty soon with these tools, everyone will have access to nation state level cyber attack capabilities. Large language models aren't agents. They don't have goals. They don't sort of do things on their own. They're basically there just to answer questions and extend things that you ask them to do. But there's probably 100 projects that are trying to take these large language models and combine them in ways where they act like agents, where they have goals that they follow and they do things. This is one example of a number of LLMs used to design CRISPR experiments for biology. And they're starting to get major advances. All the big labs, OpenAI, Google are all talking about, oh yeah, AI agents is where we want to go. A lot of the AI safety work has been on that agents are extremely dangerous because if they have goals, they tend to have sub-goals, which are not necessarily aligned with human values. And one analyst, Dean Ball, talking about this paper in particular, said that these agents, you can drop in any large language model and dramatically improve their performance. So he thinks that these agents are going to take off way faster than most people expect. He calls it more of a phase transition than a gradual ramp. So there's a wonderful book by Dan Hendricks called Introduction to AI Safety, Ethics, and Society, which goes into great detail about all of the risks and the current approaches to dealing with those risks, in particular also focusing on existential risks, things that could lead to the extinction of the human race, bioterrorism, nuclear weapons, lethal autonomous weapons, and cyber attacks. Unfortunately, I believe that the current approaches to AI safety are not sufficient. And so the top ones are alignment, which is trying to make an AI's goals and beliefs sort of aligned with human goals and beliefs, red teaming, where you try and force an AI to do something bad, restricting AIs to being non-agentic, limiting the system power that an AI is allowed to use, pausing or halting AI progress. I think all of these are great. All of these are worth exploring. But in the face of very powerful open source AIs, there's no enforcement mechanism for any of these. You may have the best aligned AIs in the world at OpenAI and Google, but that doesn't mean that somebody with an open source custom tuned model isn't going to be able to do whatever they want. And so I think we need a different approach. And in particular, I believe we need to take what some people call a security mindset. There's a very nice book by Nancy Levinson that sort of goes through that in today's world. Basically, if you want to have the influence of a system be safe, you need to model the overall system that's enabling the harm. So, what are the capabilities, in the world that is causing a potential harm? You need to model what the potential harms are and how costly they are in your value system. Model the capabilities of the adversary, and then create designs which provably limit the harms. So I think it's a great framework, and it's exactly what we need to do in the case of AIs. Challenge with AI adversaries is that we really don't know how fast they're going to improve, how intelligent will they become, how adversarial will they be, how much power and compute will they require, how uncontrolled will the open source models be. And so that makes it a much more challenging problem than more typical security situations. And I believe we really need to protect against the worst case outcome. And so I'll describe a number of techniques which I believe can do that. There are only two guaranteed constraints on powerful AI that a probably less intelligent species, humans, can use to control a more intelligent entity. And that's mathematical proof and the laws of physics. And the reason is that even the most powerful AI can't prove a false statement. And even the most powerful AI can't violate the laws of physics. It can't create matter out of nothing, go faster than the speed of light, make entropy decrease. So we can use these kind of core fundamental constraints that are constraints in the nature of the universe as a tool to make sure these systems are positive and beneficial. So Max Tegmark and I, a few months ago, wrote this paper that's on arXiv, arguing, giving proposals for how to do that, how to use mathematical proof and the laws of physics. And I'll go through them here and expand on a number of the things we suggested there. Let me start with provable software. So let's assume all the hardware is fine and it's all working properly. How can we make sure that the software does what we want? And mathematical proof is the key to that, I believe. And the basic aspects of mathematical proof that we're going to need here is that we have universal logical languages that can express any precise statement. All of current mathematics, physics, computer science, engineering, and economics can be expressed in these languages. Any true statement, which is true in all models, has a proof within these systems. And there are small, fast proof checkers which can check these proofs with absolute reliability. For example, there's a 300-line program for a system called MetaMath in Python, which anybody can study that and understand it, and it can prove, the 40,000 theorems or whatever in MetaMath in just a few minutes. So how do we use mathematical proof to get trusted results from AIs which we may not trust? So here's the simplest mechanism, and I'll talk about much more complex things. The first thing is we never have the human directly talking with an untrusted AI, because an untrusted AI may, try and persuade you and confuse you or, threaten you, as a lot of the current models are want to do, though they don't have any muscle behind those threats currently, but they will probably pretty soon. So we don't really want humans talking directly to untrusted models. But the human can pose whatever problem they're trying to solve, whatever software they're trying to write, whatever system they're trying to build. If they can describe their requirements in the precise language, one of these formal logical languages, they can give that problem to the AI. The AI is able to use whatever techniques, untrusted, potentially dangerous, potentially faulty, whatever they want, running on untrusted hardware in an untrusted country, whatever they're doing. If they can find a solution to that problem, we require them to not only return the solution, but also return a proof that it is correct within that formal system. The human then receives the purported solution and the proof. They use their reliable proof checker to check that the proof is correct, and now we can trust the solution. And so in this way, we can use untrusted AIs wherever they may be to help build a trusted infrastructure. So let me just go over, there are 5 formal systems that are sort of currently behind many of these formal systems. First, and they were basically invented in the order I'm going to describe here. Propositional logic arose in the 1800s, basically describes Boolean circuits. And there are SAT solvers like Microsoft Z3, which tells you whether you can find an input to a circuit that will produce a true output. Next is first order logic, which adds to the Boolean stuff. It adds functions and relations and quantifiers. And an example of a first order logic prover is Vampire Prover, which has been winning all kinds of contests for the last 20 years or so. Next level up is Zermelo-Fraenkel set theory, which adds to first order logic a relation of one set belongs to another set and axioms for set existence. This is the Zermelo-Fraenkel set theory is the foundation that modern mathematics uses in the mainstream. And there's a system called MetaMath, which sort of implements that very directly. In the computer science world, something called type theory has become of greater interest because it's closer to programming. And there's something called simple type theory, which was invented by Church maybe in the 30s and 40s, which adds lambda expressions with types representing Booleans and individuals. And Isabelle is a typical system based on simple type theory. The one that's generating a lot of excitement these days is called dependent type theory, really invented, I think, in the 70s and 80s, in which it's a richer form of types that can depend on values. And Coke and Lean are the two dominant ones there. Coke has really been adopted by people doing formal methods on software, and Lean has a lot of mathematicians busily encoding all of mathematics in it. And so both of those are good, and all of these are getting neural provers very rapidly. So the task of having an AI system to prove theorems in one of these systems is very analogous to game playing AIs. So, for example, the game of chess, and the reason that they're analogous is because both games and formal systems have precise rules, and you know when you've succeeded. You know, if you play a game of chess, you know when you win, and if you try and prove a theorem, you know when when the checker will say yes, you proved that theorem. And so the approach to solving those problems is very similar. So if we look at what happened in the game AI arena, back in the 90s, IBM created a system called Deep Blue, which finally beat the human world champion in chess. And basically, it was just a hardware search engine that just searched boards going forward with a little bit of heuristics at the end to say, you know, what was a good board position. Then AlphaGo came along from DeepMind, which beat the best human Go player, which was not amenable to search. They had to use a combination of search and a neural net to sort of learn to score the value of positions. The initial version was trained on human games, so it had a lot of human knowledge in it. But then they created AlphaZero, which just played itself. One of the big benefits of systems where you can precisely say whether you've been successful or not is that you can generate your own problems and you can learn on that. So you don't actually need training data. And Demis Hassabis very famously recently just said that AlphaZero, starting from scratch, became the greatest chess-playing entity that's ever existed in 9 hours. So we can see the rapidity with which a system can improve its capabilities in these types of things. Well, Stockfish, which was a search-based chess player, saw all what's going on with neural-based things, and they incorporated it. And so now Stockfish is the best chess-playing system out there because it has both neural and search stuff. And then somebody just recently trained an LLM on Stockfish, and they created an LLM that plays chess with no search. You give it a board position, it tells you how to move, and it's not as good as Stockfish, but it's better than most humans. And so that's a really fascinating development, and I believe we're sort of seeing a similar thing happening in the AI theorem proving space. Initially, the most theorem provers were search-based. So Vampire, which does first order, and Z3, those basically just search, and they have some heuristics for what branches to look for. In 2020, OpenAI released GPT-F, F for formal, and they trained it on 36,000 MetaMath theorems, and they were able to prove 56% of the theorems that they didn't train it on. In 2022, Meta decided to use a system much like AlphaZero. They called Hypertree Proof Search, and they also trained it on all of archive math stuff, but they tested it on MetaMath, and they were able to prove 82.6% of MetaMath theorems. And then in 2023 and 2024, we're seeing an explosion of open source provers. Lean Dojo, Lemma, Reprover, CokeGym are some of them. And my sense is that it's going to move very quickly, especially now that very powerful open source models are out there that you can fine tune on the theorem proving task. So I believe that we're going to have extremely powerful general theorem provers, over the next few years. Today's formal systems are kind of awkward because they're aimed at they're human centric. So, and what's interesting is that once you have a formal system that's powerful enough, it's equivalent in some sense to every other formal system. So MetaMath, Isabelle, Coke, Lean, all their specifications, theorems, and proofs can all be expressed in one another. And you should be able to translate transparently from one to the other. Interestingly, they haven't done that yet. It's still a big chore to take something proven in one of these systems and convert it to another. But conceptually, these things are really equivalent. And they've made them very complex from my point of view. Like they have complex fonts so that things look like mathematical symbols. They have complex syntax so it feels like mathematics. They built in all kinds of features and complex semantics aimed at making them easier for humans. That's fine, and that's partly why they have flourished, because humans feel comfortable using it. But these systems are really not optimal for AI-based systems, and so I believe AI-based systems could be much simpler and much more succinct, and that instead of optimizing for human readability and ability to do human proofs, we really should be optimizing for things like generalization. Once you prove something, can you prove more general things? Fast lookup. We want big databases of proven theorems. Can we find them quickly? Reuse. Can we take work that we've done in one area and can we apply it somewhere else very easily? Composability. Can we make components that can be composed with one another? Another trend in the formal systems literature is that because the general theorem proving has been viewed as too hard, they've tended to make specialized systems like propositional systems like the Z3, model checking, temporal logics, probabilistic models, symbolic math, neural models, program synthesis, all these things get their own languages, their own systems, their own, communities around them, and they don't talk to one another. Whereas all of these things should be at least they should be translatable into one of the universal models. And so I think that's a shift and a transformation we're going to need to see. Cryptography is really critical to security. And there are sort of three kinds of cryptography that are popular today. Public key cryptography, like RSA, Diffie-Hellman, elliptic curve, is used on the web a lot, and it's used for many digital signatures and for establishing communication between two parties that don't know one another. Unfortunately, it's vulnerable to quantum computing. And like AI, nobody exactly knows how fast quantum computing is coming. Over on the right is Google's threat model. Looks like on the order of 10 years, we're seeing very serious chance of quantum computers there. AI may dramatically speed this up. And AI may also break public key cryptography. I have a link to a paper by Boaz Barak, who's really good, who says there's really not much argument that the basic underlying principles of public key cryptography are actually secure. Next down are cryptographic operations based on the assumption that they exist one-way functions. And those are things like AES and the hash functions, like secure hash functions like SHA-2. Quantum computing speeds those up by a factor of a square root, but people mostly believe those are probably solid. But I keep asking people, well, do we really want to trust the future of humanity on somebody's, intuition as to what's solid or not? Fortunately, there's a third branch of cryptography, which is not as widely used as these, called information theoretic cryptography. And this includes things like one-time pads, if you've heard of that, or Shamir secret sharing. And these are provably unbreakable, but they're somewhat more awkward to use. But hopefully, I'll describe some ways in which we could incorporate that as the base of our cryptographic assumptions. So when people, complain about formal methods, they often say, well, creating the specs is just as hard as creating the programs. And it's true that creating specs is a challenging operation. But there's a whole bunch of reasons why. First of all, specs are easier than programs. Imagine saying what it means for a program to sort something. It's really easy to say when something's sorted. It's much harder to actually do the sorting. So there's a sort of asymmetry there. Specs can also be reused. So once somebody somewhere has written a spec, say, for memory safety, then that can be used in every other program. Specs can be composed. So if you have a spec for memory safety and a spec that says no infinite loops, you can just say, yeah, I want both of these to hold. Specs can be written by experts and then used everywhere. So you can have organizations like NIST, which puts out standard specs for typical security requirements, which then can be incorporated. Specs can be proven compliant with more general specs. And I think that plays an important social function where we can have governments. The Biden administration just came out with a thing saying we should use memory safe languages. In other words, everybody should switch from C and C++ to Rust, but there's no teeth behind it. And how are they going to know? So I think in this framework, there are ways to do things like that. Specs can be AI generated using auto-formalization. So an AI can read a written description of what should happen and create a formal spec from that. Specs can be AI generated from examples together combined with properties. Specs can be interactively created using provable queries, and specs can be AI generated from multiple parties' inputs. So let me just try and give a sense of the transformative implications of AI proof, because when people think about it, they're often looking at what today's formal methods do. In today's formal methods, you have some software that some people wrote. You bring in the experts, and they look at the software, and they, over laboriously over months, they figure out how to write proofs that this code really does what it's supposed to do. And then when they're done, they check it. Oh yes, it's good. And then they run the code, and everybody's happy. But it's expensive. These experts are hard to come by, and what's the benefit? The first obvious benefit is correctness. Now you're sure the code is correct. That's nice. But the engineers that wrote the code are pretty sure it's correct, and they can do unit tests and they can try it out. You can get certain levels of correctness without the difficulty of a formal proof. And I think that's why most software today is not formally checked. Now, if it's in a situation where security is important, now if there's like a 0.01% of inputs are flawed, that may not hurt the correctness in normal use, but an adversary can find that flaw, and that can be absolutely critical. So much more security critical code is formally checked. And that gets really extreme when it's hardware. So like chip design, if there's a flaw in a chip, that's a total disaster. And Intel ran into that in the 80s. They had a flaw in their arithmetic unit, and they had to, recall a bunch of chips and replace them. And so Intel hired a whole bunch of formal methods people. What I'm arguing for here is not that model of doing this formal checks in advance and then certifying it, but rather including proof generation and proof checking as a dynamic part of normal operation of these systems. And so we not only want just correctness and security, but we want certificates of correctness and security, which can be then given to other people. And so there's a social mechanism whereby the certification means a lot more than just I'm convinced this is safe, but rather I can convince somebody else that it's safe. And it means that we can trust work that's done by untrusted parties or by AIs, and we can compose multiple independent systems with high assurance. So I think those are all properties which dramatically change the nature of systems which are proven. So now let me move to provable hardware. Let me give a few examples of how terrible today's hardware is. Here's an AI system that from the sound of somebody typing a password on their keyboard, it can figure out what the password is. And how does it get the sound? Well, it could hack into a cell phone nearby, listening to the typing. It can bounce an infrared laser off your window and get, and from the reflection, it can get the sound. And so basically, today's password-based cryptography is totally insecure, and once we have somewhat more sophisticated systems, that it's going to have to disappear. Rowhammer is a terrible example of today's sort of flawed hardware where you think, our memory chips, you read something and it behaves in a reliable and predictable way. Turns out if you access today's memory in the wrong way, you access the rows on either side of one row in the memory chip, you can flip bits in the middle. And so people have used that to break into systems. And that one is a real bear to fix. For humans, you need to make sure that you never do a memory access pattern that triggers the rowhammer stuff. And so I think that's an example where you need formal methods to show that you've done that. Hardware can be, implants can be put into hardware. Here's a guy who shows that he can put a $2 microcontroller chip, which is circled on the right here, onto a Cisco firewall. And if you don't notice that little chip, turns out it has a back door. Once it's in there, anybody can access it that knows the secret key. Turns out that supply chains these days are pretty bad, and that people are, intercepting things, hardware, and possibly putting implants into it. A lot of controversy over how extensive it is. Here's a Intercept article arguing that it's very common. Today's military hardware is insecure. Counterfeit Cisco gear ended up in military bases and are used in combat operations. Here's a really bad one, a demonically clever backdoor. Turns out by adding one transistor to this chip, these people were able to create a capacitor that if you execute an unusual instruction repeatedly, it charges the capacitor, and when you do it enough times, then it opens up a backdoor. And it's virtually impossible for a human to find that. And so you absolutely need formal methods, I believe. And it shows that fabs and manufacturing needs to be absolutely secured. So we got a lot of robots coming. This seems to be the year of the humanoid robot. I think there's like 20 of them I've seen so far. Aerial drones are becoming very important. The war in Ukraine is showing that. Miniature drones are here, autonomous land vehicles, drone boats, submarine drones. So we've got a lot of AI-driven hardware out there in the world. We've got to make sure that it doesn't do bad things. Today's physical lock infrastructure is a complete disaster. There's a really hilarious, kind of shocking and hilarious YouTube channel by the Lockpicking Lawyer, in which he shows that every front door of every home in the country can be opened with a couple of taps. They can open most U.S. stores using a simple tool. A lot of safes can be opened sometimes by just slapping them. These slash-resistant bags can be cut with ordinary knives. Most cars can be opened. So we're really in a disaster in terms of physical security. So how do we use mathematical proof for hardware security? We need to do that as a formal physical world model, formal model of the adversary, a formal safety specification, and we create a formal system design which is provably safe with respect to those models. And the formal physical models tend to come in stacks. Over on the right here, I've got a picture of the stack that's involved in doing a chip design, where you sort of have architectural designs, functional designs, logical designs, circuit designs, physical designs, tape outs, and they have formal models at each of these levels. And the hope is that the model at a given level is justified by the model below it. And all the physics works this way too. So optics has geometric optics and gets down finally to quantum electrodynamics. Mechanical engineering, if you're trying to build a bridge, you have models for, what kinds of beams you need and how strong they are. All of these models eventually bottom out at physics. And fortunately, we know physics. We know the standard model of particle physics and general relativity is all described in this one equation. And for energies which are less than 10 to the 11th electron volts, and if you're far away from black holes, neutron stars in the early universe, this equation completely describes the phenomena, say, in the solar system. There's a great paper by Sean Carroll arguing all the details of this, and this is the picture he has. We don't know the underlying theory, a reality of everything. So there might be string theory or, cellular automata or something down underneath this core theory. But the physics of everyday life does not depend on those except through the core theory. That's the contention, and you can read that paper to see all of it. There may be other forces and unknown astrophysics, but those don't apply in the regime that we're operating in. There are various constraints from the laws of physics, symmetries, conservation laws, the locality of interactions, computational limitations. There's a really nice analysis by Seth Lloyd that the entire visible universe has 10 to the 80th particles. And if you treat the entire universe as the most efficient quantum computer, it can store only 10 to the 90th bits. And since the Big Bang, it can only have done 10 to the 120th operations. In the solar system, there are 10 to the 57 particles, and it can store 10 to the 67 bits and only have done 10 to the 83 operations. And so those numbers give us upper bounds on what the computational capabilities of a powerful AI could possibly be. We need to do physical security in a composable way where we can build components that we can then combine together. And some of those sort of core capabilities, I believe, should be there are trusted sensing, trusted computation, trusted memory, trusted communication, trusted randomness, trusted raw materials, trusted actuators, trusted ability to delete and destroy things. From these, you can build more complex components, such as the ability to do tamper sensing, have a very high confidence that if somebody is tampering with your device, that you'll be able to detect that. Trusted provenance, that you can know what the entire history of something has been. Trusted 3D printers, trusted manufacturing, trusted supply chains, trusted networking, trusted energy encryption, ways to hide energy in a way that an adversary can't extract it. Trusted robots. Let me give a few examples of mechanisms for doing this. So, we've seen a lot of examples of backdoors and hidden implants. How do we make sure when we build something that some adversary, some sophisticated AI that's developed nanotechnology or whatever, can't have hidden within our, raw materials, its own little devices? Well, melting is a really good way to do that. That it turns out that steel melts at 1500 degrees centigrade. And the strongest chemical bond is this weird protonated hydrogen dinitrogen. And all structure, all chemical structure is destroyed at 10,000 degrees centigrade. So if you're really worried about adversaries, if you just melt whatever you're using, then you can be guaranteed there's nothing left in that. And then you can build up from that to build things that you do trust, and you have absolute guarantees of trust. Here's a very nice system that somebody has developed for detecting attempts at tampering. Basically, you put whatever your system is inside of a radio frequency container, and it could be either at the chip level, at the module level, at the board level, at the device level, at the room level, building level. And then you send radio waves out, and then you sense those radio waves, and you learn the signature of whatever enclosure it's in. And then if something changes, somebody tries to break into the thing, you notice that in the signature. And so in their experimental results, they found that it could detect 16 millimeter insertions of a needle with a diameter of as low as 0.1 millimeter. So that gives a kind of a bound on what this very simple tamper sensing mechanism can detect. Apple has done interesting work on creating secure processors. They have something called the Secure Enclave that's currently in the Mac, the MacBook, the iPad, the iPhone, in the Apple Watch, which shows how small and cheap these things can be, Apple TV, HomePod. Built into it, it has a truly random number generator. It has a unique ID, which is not accessible off chip, so it can be used as identity. It has hardware AES encryption. It supports encrypted memory, and it has a certain level of intrusion detection, physical security. A very powerful principle is zeroization, which is that if a system detects that it's being tampered with, somebody's trying to break into it, it can delete all its cryptographic keys. And so the attacker may be able to break into the system, but he can't get any data that's in there. And you can extend that to not just deleting keys. You can also say blow fuses at an actuator. So if you have a robot that somebody's trying to take over, if it detects tampering, it destroys its actuators, basically. Or in a biological context, it can mix acid with biological samples. And so here are some examples of how you can compose some of these capabilities. If you compose tamper sensing with zeroization, you get a little module that can do computation, it can communicate, can do encryption, in particular, can do information theoretic encryption. That's something I call a provable, or Max and I call a provable contract. So it's something that you can be absolutely sure it's doing the computation that you think it is, that it's got the information you think it does, and you can operate basically a whole network on the basis of these little provable contracts. A provable secure network combines a provable contract with appropriate information theoretic cryptography. Provable provenance involves provable sensing combined with a provable contract. Provable robots involve a provable contract with secure actuators. Provable materials involve melting and distilling, and then you do your manufacturing, say, by a 3D printer. And then you have provable provenance to follow that manufactured device to, so there was no opportunity for somebody to insert an implant along the way. Provable manufacturing can use provable robots with provable materials. Provable supply chain involves provable manufacturing with provable provenance. And so you can build up a whole infrastructure such that you're very confident that all of the pieces are doing what they're supposed to be doing. If you don't want to go fully all the way to, melting everything at 10,000 degrees, you can sort of estimate what the capabilities of your adversary are, and do the appropriate level of security against that level of adversary. But you may want to increase the robustness of that in case you've misestimated it by using redundancy. There are a bunch of ways of doing that for shielding, data to keep data from escaping by side channels, or for tamper sensing. You could have multiple nested enclosures. And so if somebody wants to get at, the processor in the middle of the room, they have to get into the room first. And so you can detect it at multiple stages. Sensing can have multiple overlapping sensors. They can use different modalities: optical, radio, acoustic, thermal. Storage and communication can use something called Shamir secret sharing, which allows you to take a piece of information and split it, say, into 10 pieces, such that you need at least 7 of those pieces to reconstruct the data, and anything less than 7 will give you no information. Computation, you can use redundancy, do the same computation multiple times. There's all kinds of zero knowledge ideas and multi-party computation. Noise sources, you can whiten noise using cryptographic hash functions. You can XOR multiple sources of noise and get better noise. So there's lots of ways of increasing the capability at the expense of spending more, basically. using this provable software and provable hardware, we can create new provable social mechanisms, which I think can solve many of today's social problems. So let me just briefly hint at this. And today we often use social mechanisms which rely on humans having recognizable faces, gaits, and voices. AI agents can clone any of those, so that's no longer going to be a reliable, identity. Humans who act morally, you think they're more likely to continue doing that. For AI agents, not so likely. Humans care about their reputations, and so that serves as a really restriction on bad behavior. AI agents can synthesize reputations. With humans, social proof. Other people think they're doing good stuff. People really like that. AI agents already, people are using AI agents to create fake followers to get more social proof. Humans want to avoid being arrested, being thrown in jail. The death penalty is the ultimate terrible thing for a human. The AI agent just makes copies of itself. So you put some of its copies in jail, big deal. Humans are very hard to coordinate in groups. And so a lot of blockchain is based on that it would be very hard to get a bunch of people to do the one thing. AI agents, you can easily coordinate. Humans often give off signals that they're lying. You can sort of detect that. AI agents, they can deceive undetectably. In fact, a lot of the current systems are pretty good at deception. So we can't use today's human mechanisms of, arresting, the threat of arrest and judicial judgment and so on. Instead, we need guarantees rather than imposing costs after the fact. And so I think there are a whole bunch of provable social mechanisms. Let me just give a quick little taste of some of them. Today, we have a choice between privacy and surveillance. But in the provable world, we can have provably controlled sensing, like a camera that never leaks any information unless it sees a gun. If there's a gun, then it'll send the video feed somewhere. Today, there's a lot of talk about keeping humans in the loop. Like if an AI is shooting a gun, you want a human controlling that. Well, humans are manipulable, and so that becomes a weakness of a system. Instead, I think we need to shift to the idea that humans create the loop. You design what the rules are for the system, and then those rules are provably executed. Today, we have humans in the factory, but humans are a vulnerability. So instead, I think we need provable robots and possibly combined with human teleoperation. Today, we use biometric identity, fingerprints, eyes, and so on. That's not going to work with AIs, but we can create provable contract identities and together with provenance to get the same kinds of effects. Today, we have a whole bunch of social dilemmas that are causing all kinds of problems in that individuals have incentives to take actions which don't lead to the best outcome for everybody. With these provable contracts, we can also have provable contracts that are jointly constraining multiple agents. And so we can solve basically all social dilemmas. Today, we have laws which people are supposed to follow, but often they don't. In the provable world, we can have meta contracts which are guaranteed to be followed by anything which is governed by them. Today, we have corporations which are, by law in the US at least, are profit maximizing. That leads to all kinds of bad side effects often. We can instead create social benefit entities in which the maximization includes externalities and it serves to act for the good of all participants. Today, we have all kinds of arms races which lead to bad outcomes. In the provable world, we can create guaranteed joint agreements. So what happens next? If we stick with today's sloppy technology, I believe we'll see increasing AI-powered cyber attacks, disruption of critical infrastructure, social media getting worse and worse, AI-powered crime, AI-powered politics which ignores the true needs of citizens, greater environmental damage, and a race to the bottom. If instead we start building this provable technology and we build it up in a smart and intelligent way, then I believe we can eliminate cyber attacks. We can create reliable infrastructure. We can create media which enhances our humanity. We can create peace and prosperity. We can empower citizens. We can rebuild the environment, and it will lead to long-term human flourishing. And so I think the choice is ours, and the choice is clear. We should choose the path of human thriving, which is provable technology. So that's it.
Thanks so much for the interesting talk and vision. I suggest now we have 15 minutes left. We could have a few questions, and perhaps the easiest is if you raise a hand with the raise a hand feature, and Steve could maybe say your name and if there are many questions. Yeah.
Great. Looks like Johannes?
Yes, can you hear me?
Yes, perfect.
Okay, so the first question I have is, for example, you talked about rowhammer and formally verifying it, that it doesn't happen, and that seems to me a really hard thing. And then I have a bunch of other questions, but maybe that's the first one.
Yeah. So, I mean, that's, I think, a great example where it's really hard for humans, right? There's certain patterns of memory access which are bad. Whereas
the thing is that in your formal methods, like if I have lean and I model my system, my hardware system in lean, then the model that I have in lean is maybe not modeling physics at a low enough level such that rowhammer is even a thing that I could think about in the formalism. I think that's the problem, and that's the problem for the machine also.
Well, so that just says that that's not the right model for that system. You need both that level, right? You kind of get a level which is you got the right computation, but you need a level below, which includes this fact that this rowhammer is really bad. And now that's a constraint on the AI generating code. That code must never generate the bad memory sequence. And that's a tricky constraint, but that's the sort of thing AI should be really good at generating.
But we don't know how to have the formal model yet, right?
Well, it's pretty easy to express. I mean, like they know what, at least they have a model for what current rowhammer, the bad sequences are, what the bad memory access is. I also mean that in the sense of like,
if there are... Okay, for more questions, I will let other people ask also.
Okay, Quinn?
Hey, Steve, good to see you.
Great to see you.
About the, you mentioned that there's a possibility of a universal language that can like unify probabilistic and temporal logic, and it doesn't care about simple type theory versus dependent type theory and things like this. And this is like mildly implausible to me, but the thing that's like strongly implausible to me is that you'd be able to get them to talk to cryptographic protocols, ZK protocols and MPC protocols, like famously have restrictions on their expressivity that are different from the restrictions in logics, right? So like there's a specific like subtype of logic that a ZK protocol can work with, and right. So this to me seems like a bottleneck.
Well, so the key thing, and this is an important insight, is that, say, Zermelo-Fraenkel set theory, that's the one the mathematicians sort of started with, it can encode any other system. You can embed the system in, just by representing what are its constraints, what are, what are the properties you need in the ZK thing. The cryptographic world is actually really good at doing things in a provable way. Bonnet at Stanford has a wonderful textbook which goes through all the cryptography, giving precise definitions of what everything means and the math and the proofs of doing that. All of that should be pretty easily encodable in, say, Lean or in Zermelo-Fraenkel set theory. So it's not that the logic of Zermelo-Fraenkel set theory is the logic of ZK. It's that you represent whatever the ZK system you're interested in. You represent it as sets. And then you prove things about that. And same for probability. Probability is just, is very easy to express in using real numbers and so on. And so it's very easy to encode that in Zermelo-Fraenkel set theory.
Yeah, but real numbers in a cryptographic protocol is like a huge problem. I mean, like you need some abstraction that like is going to be leaky.
You need to distinguish the reasoning about the system from what's inside the system.
Oh, well, sure. Yeah.
Okay, Johan?
Yeah, hi. Thanks so much for this incredible talk. There's a lot to learn. I actually had a question more on the practical side rather than on the theoretical side. So of all the different, provable systems that you talked about, like provenance, secure network, like provable social mechanisms. So a lot of the reasons why we don't use those today might be due to network effects. Let's say we started out with RSA and then a lot of the internet was built on RSA. So now, we use RSA, whereas ideally we should have started with the information theoretic, provably unbreakable system. So of all the methods that you've suggested, are there systems that I mean, so let's say at some point we want to switch from the current systems to the provably unbreakable systems. If it's just network effects, then that's one thing that we can maybe convince the international bodies and national organizations and governments to do. But if it's something that is a question of, practical issues with, let's say, computation time or energy use in proving those systems, then that can be a challenge by which, we can never adopt those like provably unbreakable methods. So from all the things that you've mentioned, are all of them currently just constrained by network effects or not adopted due to network effects, or are there pieces of those provable systems that also have like practical challenges that might be hard to solve and thus hard to adopt?
Great question. This is a really critical issue. Today, people have been trying to push formal methods since the 60s. I mean, mathematicians saw it was obvious. This is the right way to design things. And yet they've had barely any impact. And the reason is it's really hard for humans to do this. So the thing that really enables both this technically and also the network effects is that I believe we're going to have AIs that can do it. Now, the current AIs are just barely getting there. So the constraint to making this actually practical is that AI systems actually get where they can say generate, provably correct code, provably correct systems, provably correct cryptography, in a matter of minutes. And whereas if you had to have humans, it'd be like a year to make an operating system be provably correct. Somebody did that, and it was a long, difficult project. So I think we have that, and then we also have the network effects. But I believe attacks are going to start happening. That's going to create. They're already happening now. There's going to be a call for the current technology is not working. We need something different. But I don't exactly know how it's going to unfold. So that's a very interesting point.
Got it. I guess for me the only unknown is even if AI can do it in a short amount of time, will the energy usage and things be practical enough that it can be done at scale? But like you said, that's something we'll only have to know when we come to that problem. So anyway, thanks so much.
Yeah, I don't think there should be any inherent extra expense. A provably correct system actually can often be more efficient because it can do things a human wouldn't do, for example. Raphael.
Hey, Steve.
Hey.
Good to speak in person after so many interactions over email.
Yeah.
I'd like to. I wrote a longer comment here on the chat, but I'm thinking of this as sort of a regularization problem, where it seems to me that the emphasis on proof is really an emphasis on trust by proxy, right? You believe that X is true, so you believe that things are built on X are true, and that's that's great. That works as far as it goes, assuming that the foundations are solid, right? And
yes.
And that's great as far as it goes, right? The thing is that there's two different kinds of trust, right? If you're thinking of the end goal, which you're proposing, which is to create trustworthy systems in general, then there's two different kinds of trust. There's that kind of trust, which is ultimately you trust that the process that generated that thing, that it's authoritative, it's outside of your control to say that it's right, but you believe that it's right because you have some heuristic reasons in your mind that have been shaped by previous experience. The other one is trust by understanding, right? By being able to reason about the thing yourself and be sure yourself that that thing as a whole makes sense. And this is what I mean by regularization. That if you want that kind of trust, which I argue is more robust and resilient, then you need some simplicity regularization, right? You need to be able to you can't just offload all the cognitive burden to AI, because that's going to give you something that in all likelihood is going to be buried. Is going to have a ton of assumptions that at the very least are going to be non-comprehensible to you, buried in there. So I think there's and I'm saying this from a perspective of somebody that wants something like this to work, but I think we need to be cognizant that there's a huge and very important in practice tension between these two different kinds of trust and the two different kinds of systems that are entailed in building this. And I just wanted to highlight that, like when we're thinking about like putting this in practice, we need to pay attention to the kinds of stuff that you know Taleb talks about in terms of convexity and anti-fragility and legibility and heuristics, all these kinds of things that we know already from all the domains where risk is something that's managed in practice, like finance and physical safety and so on. And we can't lose sight of that.
Yeah, I totally agree. I think that's a great point. I do think that if we had really good AI theorem provers, that can be used as a tool where you can say, does this thing guarantee this property? Oh, it does. Does this thing guarantee that property? So you can sort of, even an impenetrable system you don't really understand, if you had a good AI theorem prover, you can probe it and get more understandable things out of it using that tool. So I think the two approaches are good.
Maybe for some people that would be enough. They can trust the AI system enough that it can then trust by proxy
No. We're not trusting the AI system. We're forcing the AI system to give us a proof that we can then check. So we never put the trust on the AI system. We always have it based in mathematics. Now, of course, it has to be.
You have to trust the checker, right? You have to trust that this.
Oh, but that's easy. That's 300 lines of Python. So I think that's not a problem. Trusting the foundations, that's more of an issue. Yeah, we can talk more about that later. Yeah.
I think we're coming out of like this reality fork where people are being asked to trust that there's such a thing as COVID-19, and they can't even they can't even bipartisanly agreed on these kind of like very basic facts about reality or about like statistics, right? What does epidemiology actually say?
Yes.
And so on. So I think there's some like really foundational aspects having to do when we get to the practical side of it.
Great. Johannes?
So yeah, just to say there's like 3 minutes left, so we could take one last quick question and then end the session.
Yeah, maybe I have a question. Sorry, I couldn't find the button.
Kim, yeah.
Thanks, Steve, for the talk. Just going back to the paper you originally wrote with Max, you stated some challenge problems, and it's quite a long list, everything from tooling to benchmarks to, specifying some complicated stuff. Just maybe from your own point of view, like what do you have a favorite, or do you have one that you think is most practical for folks like us to think about, either pushing for, getting funding, things like that? Because it was a long list.
Yeah, that's a great question. I mean, for my thinking, I think that having really powerful and easy to use theorem provers is the sort of bottleneck for all of this. And so what would be really beneficial is taking, say, the existing theorem provers, like there's something called Reprover and open source ones, maybe on top of like the Llama models, so the new powerful open source, and applying it to one of those tasks. A simple proof thing that would sort of get the ball rolling of, oh yeah, here's how to do it, and it's free, and you can run it, and students can do it. It doesn't have to be an esoteric phenomenon. So I think that would be really, really valuable. And then in terms of actually doing something which itself has economic value, I think there's a bunch of those. There's tons and tons of money is going into cybersecurity right now. And I think the current methods are pretty bad in some sense. And so as that heats up more, I think things from this world will suddenly have great value.
I see. Cool. So kind of tooling and then maybe targeting security could be one. Great. Yep. Thanks a lot, Steve.
Great. Well, thank you all for coming.
Yes, thanks so much. So we'll see each other for another session next month on the second Thursday of the month. And yeah, round of applause for the great presentation. Yeah, thank you.
Thanks, everyone. Thanks for setting it up. Have a good day.